In this video, we are going to talk about inverse normal distribution. So inverse normal distribution is just when we're given the area or the probability underneath the curve and we want to find that boundary instead. So with normal distribution, we were given that boundary and we wanted to find that area under the curve. So now it's reverse. So on the picture, what it looks like is we're given that shaded region and X that boundary we want. So our calculator steps, again, it's all in the calculator. Second bars, go down 2 times to inverse norm, press enter, fill in your info, and then go down to paste and press enter 2 times. Now, special thing about the area underneath the curve. So always use the area to the left of the wanted boundary. Here's the thing. Your calculator, if you have a newer one, will let you do area to the right, but the old school dinky calculators that you'll have to use for the IB exam only do area to the left. So it's best for us to be in those good habits of always using area to the left of the boundary. So on this first example, we have X squiggle in 21,9, which means a normal distribution with a mean 21 variance of 9. We want to find our X boundary, which is the lowercase x. So we're saying what's the probability X is greater than this boundary. So we are technically shading to the right, and that value is 0.4. And then the mean is 21. So again, we want the area to the right or to the left. So we have the right. So to get that area to the left, it is the complement. So 1 minus 0.4, which is 0.6. Putting it in inverse norm, our area is 0.6, mean is 21, and then our standard deviation is 3 because, again, in our normal distribution notation at the top, we are given the variance, which is omega squared. So take the square root, and that's how we got 3. Put that in the calculator, and our boundary is 21.8. Our next one, we need boundaries A and B. We're given that middle space between A and B is an area of 0.68. So we need the outside, so 1 minus 0.68 is 0.32, and then it says they are equal distance, so divide by 2, and we get 0.16. So drawing that out, we have boundary A and B, and on either side, that area is 0.16. So starting with A, because we have that area to the left of it, we have area is 0.6, mean standard deviation 21 and 3 still, so A is 18. Now for B, we have the area to the right. So getting that area to the left, we do 1 minus 0.16, put it in, and we get B to be 24. So for our next one, we're talking about cauliflower. This first one is just norm CDF, finding that probability and multiplying by 400. We want to see how many of them are small, and they are classified as small if they are less than 750 grams. So our squiggle is to the left tail, so our lower is negative infinity, so negative 1 E99. Our upper, our shading stops at 750. Our mean is 821, and our standard deviation is 40. So our probability, we multiply by 400, so the expected amount of cauliflower that are classified as small will be 400 times 0.0379, which is 15.2 cauliflower. The heaviest 8% are classified as oversized and then repackaged. So that one is an inverse norm where we have the top 8%, so 0.08, which means the area to the left is 1 minus 0.08 or 0.92. So inverse norm use 0.92, mean and standard deviation are still 821 and 40. So 877 is that boundary. So finding that range, we are more than 877 grams to be considered oversized. So our next one is an IB example. We're talking about times that students come in come in the morning. So the mean is 52 minutes after doors open. What's the probability that student comes 60 minutes after class? So our lower is 60, upper is positive infinity. Mean is 52 with a standard deviation of 5. So the probability X is greater than or equal to 60 is 0.0548. AII wants the same thing, but between 45 and 55 minutes. So our lower bound is 45, our upper bound is 55. Mean and standard deviation are still the same, so that probability is 0.645. Now, our second school has the same distribution, we're given that 15 students arrived at least 60 minutes after school opens. So since it is the same distribution, it means the probability is the same. So we're going to use that probability to find how many total students are at the school. So we know the expected number is 15, and the expected number is equal to n, the total amount of students times that probability. Well, at least 60 minutes, that was our answer from part AII. So 15 equals 0.0548 times x, which is 274 students when you divide 0.0548 to the other side. Our last IB example on this one, we're talking about the top 10% of students. We need to find that score, which is K. So the left side is 90%, so inverse norm 0.9, mean is 300, standard deviation is 100, and we get the K boundary to be 428. Now for part B, Marian College only accepts those who have at least 450. So our lower is 450 with an upper of 1E99, aka positive infinity, still a mean of 300 with a standard deviation of 100. And we get the probability that our score is at least 450 to be 0.0668. And then last, part C is a given condition. We are given that Naomi attends Marian College, which means she did score at least a 450 on the test. Find the probability she scored at least a 500. So that will be 500 given that it's at least a 450. So for the numerator, our lower is 500, our upper is 1E99, mean 300, standard deviation 100. So that probability is 0.022. We found the probability of 450 in part B, which is 0.0668. So the probability that Naomi scored at least a 500 on the test given she got into Marian College, aka scored a 450, is 0.341.